Hello everybody, my name is Christian Pacheco. Today I'm joined with my teammates, Abdulaziz Almosa, Drew Camplone, Michael Tyler, and Cooper Hobbs, and along with our technical directors, Mark Rodriguez and Dennis Galpo, we formed Team Infineon. And the project that we've been tasked with is creating a Generation 2 Spec tester. This stands for a System Power Extended Cycling System. So basically, the motivation of this project is to improve current testing methods for DC-DC buck converters. Basically, a buck converter or step-down converter is used to take a larger supply voltage and step it down to a smaller regulated voltage. You can see here we have our supply voltage, output voltage, and the power phase, which is essentially just two MOSFETs, a high side and low side MOSFET, which are controlled by a phase controller or pulse width modulated controller to modulate a square wave here at the switching node. Essentially, to simplify, the pulse width modulated signal is time averaged by an LC low pass filter here at the output. This yields a simple steady state equation where the output voltage is simply the duty cycle product multiplied by the supply voltage. So for example, if you had a 10 volt supply voltage and a 20% duty cycle, this would yield a 2 volt output. So basically, maintaining a steady regulated output voltage at steady state is quite simple. However, problems arise when you encounter large load transients. As you can see here, we have our steady state duty cycle output at the switching node. However, when there is a very quick load transient, you can see that there's the output capacitance is drained due to the regulator not providing enough current immediately. This causes drainage of the capacitance at the output node. To compensate for this, the phase controller takes the steady state duty cycle and increases it to increase eventually the average output current. This will recharge the output capacitance and restore the output voltage. Now, any sort of testing platform must be able to take these devices and pass them through a range of conditions. It's important to do large-scale testing of a large number of devices through a large range of conditions and compare the results to aid in innovation within a competitive industry. Now, currently, we have one mainboard setup, which is technically a neighborhood of 10 devices within a 60-device system, which we aim to reach. This has 10 distinct testing modules. You can see here that we have one module already filled. This functional mainboard, it works for testing, but it is not capable for full data collection at the moment. Here you can see a close-up of one single module. You can see that it utilizes a set of sockets, 3 sockets, to allow us to easily change the device being tested or other hardware components without replacing the entire main board. You can see the 3 main hardware components here. The load board, which has a DAC on it, which allows the user to generate custom current transients. This also has the phase board, which is the part of the schematic I showed you earlier, which is controlled by the phase controller, which is the device under test. Now you can see a quick diagram of one single module here. You can see that we have the load board, phase board, and phase controller. Now both the phase board and load board generate quite a bit of heat because they dissipate quite a bit of power. So there's a full-size PC processor fan located on the back side of the load board, and a separate fan that blows across both sides of the phase card. Now I'll hand off to Aziz to talk about our investments.
Thank you, Chris. So by April 13th, we anticipate to have implemented a system that is capable of monitoring and managing one entire neighborhood that can be later on expanded to manage all 60 devices. We will be designing a fan control board that will have thermal management and monitoring of local cooling fans. The system will be able to control and collect data via user interference so that it will control the load, detect faults, and send notifications. So here's an overview of what our best anticipated outcome would look like. The FPGA pulls data from the 6 main boards and sends it to the GUI that we will be designing. And at the same time, the fan control board will be managing exhaust and intake fan speeds based on temperature sensors that are placed throughout the server rack. And from that, the fan data will be sent to the FPGA so that it can be transferred to the GUI. And with that, I'll pass it off to Peter.
Okay, so for technical accomplishments, first thing we had to do was become familiar with the Infineon hardware and software. As you can see, it's quite a lot of it, and it is quite complicated. So we did this using Infineon's Power IR Center GUI, connected all of these devices using a USB to I2C connector. And besides working with them using the GUI, we had to become familiar with the fundamentals of power electronics and the principles behind them. And that was really useful to understand this whole project. So from there, we had to characterize the load boards and become familiar with how they respond to different voltages. We expected 1 gain of output per 40 millivolts at a potentiometer measured on the load board. You can see here, we plotted that against an expected curve and was able to come up with an offset, which will later be used to basically make corrections to the load board output. And from there, we had to test the onboard fan protection, which basically turn off the output current should the fan fail for whatever reason. And beyond that, we also had to test the thermal protection, which would turn off the output current should the temperature go above a certain value. And then lastly, we need to develop an Arduino-based code to interface with the digital analog conversion of the load board. Basically, this will allow Infineon engineers to send custom current transients to the load board for testing. And this is all done over an I2C bus. And this code right here will be directly migrated for phase 2 of our presentation, of our project rather, which is FPGA integration into the entire spec testing platform for data consolidation, fault management, temperature measurement, fan control, and lots of different things. And just to give you an idea, this is a block diagram of one of the neighborhoods, which there are 6. There are 10 sets of devices, load board, phase board, and controller per neighborhood. All of these will be connected to that one FPGA, and currently we anticipate we'll only need one FPGA for the entire project, so we'll update as we go along. So from now, I'm going to hand it over to Mike, who's going to talk about the software aspect of this project.
So this is a basic idea of our user interface that we're going to be using to integrate with the hardware. So off to the left here, you can see it's split up into 3 sections. One section's for the individual hardware. So what a user would do would be able to select one of these devices, 1 through 60, and send direct codes to that device based on the neighborhood. The next block is the neighborhood off the left over here, which is split up into 6 sections, and it would control the 10 boards meant for that neighborhood. So neighborhood control 1 would control all 10 devices for that neighborhood. And then the master control seen at the top is meant to control every single device, so 1 through 60. So once a user clicks on any of these icons, a pop-up would appear for the control box. It's a basic checkbox display, so once the user checks off what they want to test, that test would be sent to the hardware. Some of the other features that we want the hardware to have is display telemetry data, monitor status, and flow reports, and control and monitor temperatures by controlling the fans. I'll pass on to Cooper now to talk about the database.
Thank you, Mike.
So the data collected by the FPGA will be imported to the PC by USB. It'll be imported into Excel, and from there into Microsoft Access, where we will create a database for it. The database will allow for the automatic generation of reports summarizing the collected data, and the interface of this database will allow its user to create reports for, on multiple metrics and to select the data that's pertinent to them. And finally, we'd like to acknowledge the Infineon staff, including our technical directors, Mark Rodriguez and Dennis Gallipo, as well as Dan Clement and Daryl Gallipo for their continued support in our endeavors. And we'd like to thank Dr. Sunak, or without whom the Capstone program would not be possible. Thank you.